All right, everybody, I hate to break up all the good conversations that are going on, but we have two more talks to finish up today. So if we can all start making our way to our seats, and then we can pick up these conversations afterwards. All right, thank you. And with that, I'm going to turn it over to Prasad and take it away.
Thank you, everybody, and thanks for this opportunity to speak here. We have been speaking about ARD data for last 2 days, and here is a good example of what we can do with an ARD data. When we talk about ARD data, as some of the speakers have given, what does that mean? You know, does it mean that it is radiometrically corrected, geometrically corrected, or is it top of the atmosphere reflectance or ground reflectance? And so, you know, that kind of a thing varies, you know, depending upon what it is. So in our product, if you talk about ARD, we talk about mostly surface reflectance product in most of the cases. In some parts of the world, we might have used top of the atmosphere product because of certain reasons. So what I'm going to speak over next maybe 30 minutes or so is to give an overview of global croplands and how we did this using Landsat, and at least for Africa, we also used Sentinel data, nearly 36,000 Sentinel images. So this is a 30-meter global cropland extent product, and for all higher level products, getting a good global cropland product at 30-meter is very important. I want to start off with a thought from the father of the Green Revolution, Norman Borlaug, and you can read that there. The main thing here is that in order to understand food security as well as water security, we need products such as this. That is, at a very high resolution, we need products of global cropland and global cropland water use. But since agriculture consumes nearly 90% of all human water use, and remote sensing offers the best opportunity to estimate crop water use, here we go that, you know, you have the greater the accuracy of cropland product, the greater the accuracy of the crop water use assessments that we come on. And both of that very much required for feeding the populations of the world. And just I think I'm going back. Just an thought here about what has happened in terms of human population and relationship to the agriculture. You know, there has been from 1950 to 2018, there has been nearly 8 times increase in croplands and nearly 6 times increase in cropland and 8 times increase in irrigated areas. And irrigated areas is where you can produce more crop per unit area. And of course, the carbon emissions related to that, nearly 10% increase, we have reached nearly 10 million metric ton of carbon 2018, and that, you know, is an important factor since agriculture contributes to nearly 30% of that is an important factor. When we started this project, we told that, okay, there are a lot of coarse resolution cropland products, but what we need to achieve is a 30-meter or better cropland product. And when we talk about cropland products, it is cropland areas, crop types, major crop types at least, crop watering method, whether it is irrigated or rain fed, cropping intensities, whether it is cropland or cropland fallows. It's an interesting product to generate by itself. Now here is an example of a 30-meter product, 1 kilometer product, and a 300-meter product. And if you just focus here in this area in the in north of South American continent, you can see here only blips here. Of course, you have to zoom in and see, but you see a lot of this area at 1 kilometer and at 300 meters. So what it tells you is that geographic precision of where cropland exists is achieved very highly in 30-meter product compared to coarser resolution products. So I will go through how we achieved a global cropland product at 30-meter. Starting with definition, standing crops, when we what is cropland for our definition at least, and the definitions are very important. Standing cropland fallows, and basically the permanent crops. When we talk permanent crops, coffee, tea, rubber plantations, and so on and so forth. So put all of this together becomes cropland, total cropland. For example, in California land area is around 100 million acres, out of which 12% is cropland. Every year there is a 20% cropland that is left as fallow in California, of the 12 million acres of croplands in California. And so there is actually a paradigm shift in how we do cropland, any mapping these days. There is tons of satellites up there, hundreds of satellites up there from which we collect data, and we are not now talking about ARD data. And ARD data is something not new. We have been working on this for many years, and these are kind of megafile data cubes. Several years back, about 15 years back, we published a paper basically on megafile data cube and how to composite data cubes and compute croplands, cropland and irrigated areas. And machine learning and deep learning, as kind of a together, that where we, for example, in our project, there are number of for cropland, number of algorithms that we can use in machine learning and deep learning. But in our project, we have used a pixel based machine learning algorithm, supervised classification, such as random forest and support vector machines, and object based classification such as hierarchical segmentation. Actually, one of our project members, Jim Tilton from NASA JSFC, is actually a developer of this one. So we used all of these. In fact, if you look at this list, I did not put this list just for the sake of it, but actually we have used almost all of these algorithms during our project in one continent or the other. And you can see that in numerous papers that we have published. And of course, putting all of this, and when we have a very excellent understanding of machine learning and getting products using good reference data set, and then potentially the hope is that the machines can take over and self-learn and get into artificial intelligence. And all of these can come into a box, something like in cloud computing platform, and having Google Earth engine was really a blessing for us in our project. Otherwise, we would have been very slow. And of course, there are other cloud computing platforms that one could use. And I have worked over many years over hyperspectral remote sensing, which is actually my specialization, starting from when first EO1 satellite was launched. So I have good experience with how we use data cubes, especially hundreds or thousands of bands of data. And if you look at US, it's the entire world, there are around 70,000 images of Hyperion data which is available in USGS archive that anybody can use. And always I say to PhD students and postdocs that here is a goldmine of data that you could use for so many different things and actually become become marketable in job market, being a smart engineers and smart scientists really. And because hyperspectral data, for example, offers these various different things, a fascinating number of things that you could compute that are limited in hyperspatial data that you are talking about, like planet, for example. Planet data is only few number of bands, correct? So we need to fuse all these kind of things in order to really come to a good information data bank going forward. How we started our project is this way. We divided the world into 72 agroecological zones, starting with the UNFAO's global agroecological zone. We combined them into more compatible zones. There is a lot of things that are going on. I am not going into details here, but the single data use is gone, and we have hundreds of doesn't matter how many data have number of bands or number of images over time periods that you have, you can composite them, and we used nearly between every Landsat image that was acquired between 2013 and 2016 to stack and get a number of bands like blue, green, red, and sometimes 11 or 12 bands that we stacked and got either a median value of a band reflectance or an index of this band, and composited that into a data cube. And this data cube was constituted for each one of these 72 zones when we did and apply all our machine learning algorithm. And I will give an example of China and Australia. This paper just got published, and when we have this, you can see here all this, and we broke that also into various time periods in Julian dates. For example, Julian date 1 to 90 is time period 1. That is because in agriculture phenology is very important. So you composite according to the phenological cycle during the Julian year, and get all these bands of data and stack them and get that itself is quite you need to require a lot of time if people wants to understand that very well. But you have different time composite periods like time period 1 to 60, 61 to 120 days, and you have these number of bands, and finally you have a megafile data cube of 48 for each one of these 72 zones. And once we have that, cropland and non-cropland, you need to have an excellent reference data set. And we have 4 sources of reference data set that we used. Sub-meter to 5-meter data from mostly sourced from NGA, and ground data we have extensively partners around the world, and also we used some kind of what you call data collection tools from all over the world that we could collect and get the data to our servers, and secondary data which is such as for example CDL only when we know that data is very reliable for training, and the tertiary data again once we know that this data is of very high quality. And so you can see here we have all over the world, for the entire world if you spread around, that we have this kind of data spread across, that is training data as well as training data for machine learning or deep learning, and also for classification for validation. And ground data we have gone and collected data very self, and I myself have worked in some 32 countries in the world, and I understand agriculture very well across the world, and have deep understanding of different agricultural systems that is very much needed when we do this kind of work, that it's not that you can what we do at one place can be replicated at other place so easily, and there will be a lot of uncertainties in that case. So once we have good reference data set, then we use machine learning algorithm. When we talk about machine learning algorithm, I am talking here about all this set of things, but mostly we have used 2 pixel based supervised classifiers, random forest and support vector machine, in addition to object oriented classification, so that we get good objects. And of course we have used many others in certain continents. And for Africa, for example, random forest support vector machine, you can see where our training data sets are. All the things on the red are training data set, and the validation data sets that are in green. And so what happens is, this is how you select. It's not like a point, but it's more like a polygon. Each sample is a polygon, so it has been carefully selected with lot of effort and a lot of thought that has gone into this. And so the processing stream takes this course. You have 72 zones, you create an ARD like megafile data cube, and then you have this data set which is available for training, and we actually make all of this data, training data also available to people through our website. And then you generate knowledge, and this knowledge is generated for, basically you need to have a perfect knowledge to, so that it is that whatever you are trying to separate is can be separable, and that you do it through a lot of effort and looking at lot of bands and lot of time series data, and see where you can separate cropland or no cropland, or if you are trying to separate 2 crops, where can we separate this. So In this example, it's crop versus no crop, but you can do the same methodology for crop types or irrigation versus rain-fed and so on and so forth. And also, so look here, for example, all the cropland points are in red and all the non-cropland points are here. Some commissions and omissions are unavoidable. This is where this is where we need an error matrix. So what happens here is, if you take a very small area, the example is that you have a pixel based classification, this is a reference data, a pixel based classification, an object based classification, a combination of pixel and object based classification giving you the final result. And so what happens next is, this is the final product that we have for the entire world using this philosophy of how I just explained. And ultimately, in the terrestrial area, our calculation shows there is 1.873 billion hectares of cropland, which is 12.6% of the total terrestrial area of the planet is under cropland according to us in Nominal 2015. So you can zoom in, go to croplands.org and you can zoom in and you can go to any small part of the world and can look at this 1.873 billion hectares of cropland, whether they are small or big. I am not saying this is perfect, that that I will tell you why it's as good as it gets. So that is all I will say. And for China, for example, this is a product that we have, and this is for India and China. So just some zoom in views for you guys to see. And this is Xi'an in China. I was in Xi'an for a few weeks back. I made this slide when I was going there, and lot of agriculture there. And so what you see here is, these are all small built up areas within the agriculture. You can see here, just in extended area across Xi'an. And this is how it looks on the background, and this is somewhere in Germany, in Cologne in Germany, and this is the previous slide. And if you look under that green, you can see that each one of the city that is masked out, and the green area is cropland. And so if you zoom in further, this is the level of detail you see. That means every farm anywhere in the world, you can basically map it. And so it is an amazing thing to see that this is possible. And so this is a reference data, how a 30-meter product will look like this, a 250-meter product will look like this, a 1-kilometer product will look like this. So geo precision in high coarser resolution data is really bad. And also that also implies lot of things for food security and water security, how much croplands exist in terms of areas, in terms of, for example, a national systems can basically use this kind of products to bring in their national statistics, just using this kind of a data. And for all higher level products, you want to see even an individual farm, you can calculate 10 types of parameters, and all done using this kind of data, whether it is biomass, leaf area index, carotenoids, anthocyanin, so on and so forth, especially if you have hyperspectral data to match with hyperspatial data. And now let us look at the accuracy. So the accuracy was done by Russ Congleton and his group in University of New Hampshire. Russ is a known authority in accuracy, and these are the data points. Data points, of course, were gathered by us, by our team, and the accuracy goes like this. For every one of the 72 zones, we have an accuracy error matrix. For example, zone in North Africa, that means that the producer accuracy is 91.5%. That means we are missing 8.5% of cropland. So we have captured 91.5. When people show, okay, look here, that this is not captured, I say, okay, in that zone, maybe we have not captured 8.5% of the cropland out of the 100% of the cropland that you have there. And commission error, that means User accuracy 89%. That means nearly 11% which is non-cropland has come into cropland. This is an inevitable thing in any algorithm, that depending upon the knowledge base you have omissions and commissions in any machine learning algorithm. Based on the knowledge you feed in, the more accurate your knowledge, the greater and better performance your algorithms can give. Otherwise, it is just a map that has no meaning, because you can get any color map. I was seeing somewhere people were showing, oh, see, I can calculate rice just using some sample points. People don't understand that it's not that easy. You need to really understand so many dynamics within that, and that's very important to know. So it requires a lot of effort and care in how we do it. In Australia, which is much simpler case, we captured nearly 99% of cropland. Imagine that, we hardly missed any cropland. But in order to achieve that, we have 21% commission. So my philosophy when we are working in this project is, it's okay to have a little bit of commission as long as we can hit the brakes, hit the gear to see how much accuracy we can get and how much we can capture, and that I think we are able to achieve here. And we have in our website, for every zone here, you can go and check what is our overall accuracy, what is our producer accuracy, what is our user accuracy, and those interested can take a look. So, but higher level product from this product is just the beginning of a fusion of products that you can create, and baseline cropland product having it accurately is the must for doing anything else. So, I say that you need to put in a lot of time and energy into getting this one right, then the rest of the things can become very easy. And if you look at the world, look at the top countries. India has, for example, 180 million hectares of net cropland area. This is net, not the gross cropland area, which is, that is how many times you grow crop, maybe 1 time, 2 times, 3 times in some places in the world. And US, China and Russia are the other big countries in terms of cropland area. So, Russia is 155, US is 167, and India is 179, China is 165 million hectares of cropland, net cropland area. And we have this cropland area calculated for every country in the world, 200 plus countries in the world, and compare them with the FAO statistics and others. What is fascinating here is, I call Europe and South Asia the agricultural capitals of the world, because you look at Europe, everybody thinks it's the industrial country. Countries like UK, France, Italy, Germany have nearly 60% of their land under cropland. It's fascinating to see that. And countries like Uruguay nearly has 67%, Denmark, Ukraine are 75% of their land area under cropland. So it's so you can get all this kind of statistics out of this, and you can see here, and you can zoom in and see for yourself. And using this data, you can come up with lot of other type of statistics. For example, how much per person cropland you have. Uruguay is the #1 country in the world. It has around 3 hectares per person cropland, whereas US has around 0.5 to 1%. I know there is an exact figure, but I don't remember that. You can go and check that in our web page. And comparison with other statistics, with the FAO statistics for every country in the world, that you can see here. But the thing is not calculating the country statistics. The beauty of this is to calculate sub countries, and in fact, if you have village level or even farm level statistics is possible. So, for China, we calculated all the provinces of China and compared them with the Chinese national statistics. So, you can see the comparison there. It's pretty good. And dissemination, we have data can be, all our data is downloadable from LPDAC, and that's very interesting. You can view it there. And there is project websites that explain a lot of things, and this is the LPDAC site, which you can see. There is a recent paper that we just published in ISPRS. This came out maybe last week, and there is another paper that is on remote sensing, and we have a lot of other papers coming out. But before I end, I also want to show something important. For example, you can go in here and for any place in the world, and you can go in and you can you can look down here, and then if you take this off, you can see what is in the behind this, and if you toggle back and forth. What is interesting is also, if you go to this site, we have other things in the world that probably people forget that we have. For example, if you go to South Asia, just South Asia, if you focus and I de-highlight South Asia, you can see irrigation versus rain-fed in South Asia. All this red area is irrigated areas. So you can look it up, and you can zoom in and see this. Because of time, I'm not putting too much effort into this. But Australia also, like you can have irrigation versus rain-fed in Australia, that you can see those red areas are irrigated areas, and that kind of a thing. And if you look at other data products, like for example, for Africa, we have a few, 15 years data product for Africa. Like for example, what was cropland, no cropland in 2004 and 2009. All of these, for example, I clicked on 2009. Let's see whether that comes. It will come here. You can see what was it difference from other years, and this kind of statistics is available, and various different classes here also available there. And this data is here. You can see all our publications based on different years, also published here. All our LPDAC documents should be coming up here in 2018. You can see here all LPDAC has, each continent has its own user documents and all those kind of things. Then one other thing, last thing that I want to show is the statistics. How one good thing of having data in LPDAC is every month we get from LPDAC people. This is for month of June. How are people using it? For example, if you take this one product for one continent, nearly 40 users are using it, and how much data is being downloaded is also there, and which countries are using it. You can see here, and this is being month by month statistics, and who is using it and for what purpose, is also available here. So that's all I have to say. Thank you very much.
Thank you so much. And we have one more talk, and then we'll invite the presenters to come up for the panel.
Just checking, you can hear me? Microphone's on? Okay, so thanks everyone. My name is Greg Fiske, and I'm from the Woods Hole Research Center. We're in Woods Hole, Massachusetts, and while Prasad was giving his presentation, I was cruising through his application and I found us. And very well, there's a nice hayfield in our backyard, and those are the green pixels I see there, so that was very good to make that connection. So we're down here in the village of Woods Hole. I'm from a nonprofit called the Woods Hole Research Center. We have about 60 people. We have about 40 people doing science. Again, we take donations. We work with National Science Foundation money. We try to put our science into policy. The person on the left here was our director for many years, and then he went on to be the science advisor to Obama, and now he sits 2 doors down from me, so I get a lot of interaction with him and his group. Our current director is Phil Duffy. He also came from OSTP, and so it's really fun to work with these people and to see that the dynamics that are happening with their colleagues. Like I said, we try to interject our science into policy. That's not going very well these days, but we're hoping that things will turn around again sometime soon. If you know anything about the Woods Hole Research Center, this is one of our signature products. We've been working on this for over a decade. This is our 30-meter above ground biomass or carbon data set. It's going to be a urea product, but again, I've been working on that for over a decade, and I'm kind of tired of talking about it. So now I've got this new project I've come to talk about here, and I'm hoping that this will bring in some of the ARD, and I'll be able to start working with the data sets that you guys have been producing. This is a shipping track record for the Arctic. Believe it or not, we have a brand new ocean. Let me say that again. We for the first time in human history, have a brand new ocean that we can use. And this is what you're looking at here are ship tracks from AIS, satellite AIS, for 1 week in September of 2009. I like Will Cadell's quote from yesterday where he said, "Where humans move, there is value." The policy folks I'm working with say that there's going to be $1 trillion of investment in this part of the world over the next 10 years, which is just a massive amount of money. Again, it's a brand new ocean. So the data I'm working with is from a small CubeSat. You guys probably know more about these things than I do. I learned about them for the first time 2 years ago. This is the PrizeSat constellation of satellites. I have access to 4 of them right now, and I'm working with the folks at SpaceQuest. They've put up these things since 2009, and they've been selling them to Exact Earth and others, as well as maintaining these 4 right here. Our data record runs from September 1st, 2009 to actually to the present, but the data I'm presenting to you goes through December 31st, 2016. And this makes us the longest AIS ship tracking record available for the Arctic. Integrating our data with the folks at SpaceQuest and asking them questions and trying to get the answers we want out of the data available. I've learned a lot about what you can get from these small satellites. And for example, these are the 4 satellites that we're working with, and you can see that the progression of robustness and data that comes from these over the time. And all of this is kind of being funneled into what's called the Arctic Marine Shipping Assessment. So again, I work with a lot of policy folks. They don't know much about the technical back end or the data, but they have lots of questions and they're making big decisions. Again, when you're working with $1 trillion of investment, that's a lot of big decisions there. So the Arctic Marine Shipping Assessment was a report done in 2009, and this was to kind of reveal some of the intricacies between humans in the Arctic and the increased shipping activity. So this is being redone now. I'm working now on the 2nd generation Arctic Marine Shipping Assessment. And the basic theory is that as the sea ice declines over time, are we seeing an increase in ships in the Arctic? And our analysis so far has showed that you are seeing an increase in ships in the Arctic, but you're also seeing an increase in the ability to detect the ships in the Arctic. So taking that the next step further, and our challenge now is to start pulling trends out of that information. Like any data set I've worked with before, the first thing I did is go in and start digging out aspects of this data set to validate it. I spent a lot of time learning about marine activity and talking to ship captains. This one particular instance, this is the Crystal Serenity, which you probably heard about in the news, which now takes people on cruises into the Arctic through sea ice and so on. It's usually accompanied by an icebreaker. Captain Birger Vorland is the captain of this ship. And he does the multi-million-dollar trip now. He's done it twice, and he's working on a 3rd trip to go through the Northwest Passage. And indeed, I can dig into this data set and find his track, where he's been, and what he's doing at any time. I've also started to compare this with some of the big commercial satellite data records. You've all heard of Global Fishing Watch, for example. Exact Earth puts out the data for that program, and they also put it out for Barent Watch, was a program based in Norway. And I've extracted portions of our data and compared to theirs. And we always come in within 10%. So there's good validation, at least compared to other AIS ship programs. And it's unique because every time I compare our data to theirs, I find that theirs is always filtered when it comes to like military ships and things like that. Where we're working with the raw data, I can go in and I can actually find every single ship, not just the ones that have been filtered and hand off to the next company. Just some background, I'm taking this data, I'm turning it into NetCDF format. We did it initially at a 40-kilometer resolution, but now we switched to 4-kilometer and then 1 day in time. And the reason we're doing that is because we're matching it with the NSIDC sea ice. I'm using a lot of tools. I've been using Earth Engine with Tyler and his group since 2011, so I'm leaning heavily on that. Of course, R and Python for processing the raw data, Esri for making maps, and then now I've inflated the BigQuery icon because they've now enabled GIS in that application, which is pretty exciting to me. Just some quick results. This is where the ships have been over that 8-year time series. You can start to see some highways developing. Of course, you see the Barents Sea at the top, which is traditionally sea ice free year-round. And you see a lot of activity on the left side of that map, including some trips heading towards the North Pole. Over the time frame of the time series, the mean center of shipping has moved towards the north and towards the west. So it's heading towards, towards the east, or it's heading towards Russia, and it's heading towards the North Pole. This is how the folks I work with look at the northern part of the world in the Arctic. You ever question what is the Arctic? You know, as a geographer, I always say, well, so it's north of the Arctic Circle, but it's not. There's about 20 different ways of looking at the Arctic. You have the traditional areas where there's sea ice, which is either the polar cold or the non-polar cold area. You have the area within the Arctic Circle, but it usually includes the Bering Strait because there's ice there as well. And then you have the marine sea environment, the dark gray. So everything we do, we have to do it at many different extents. This is taking our entire, stepping back to those extents, this is taking our entire time series and putting it into a daily format. As you can see that the ships kind of come and go with, as the sea ice recedes in the summer, they head into the Arctic and do their fishing, shipping of all activities, and then they retreat in the winter. Another unique thing that you can see here is that the Barents Sea is a kind of a haven for the ships in the winter. They all head there to be out of the areas of sea ice, but then in the summer they bail out. I've since worked with a bunch of folks who have done fishing studies of just fish vessels in this area, and indeed they head out of the Barents Sea in the winter or in the summer, and usually following the fish. But the other aspect, and this is where it comes into working with other data sets and what's going on at this conference, is that you know, ships are a dynamic thing, and so is sea ice. This entire ecosystem is a very dynamic aspect and really hard to work in a geospatial realm like this. Sea ice moves on a regular basis. So what we did in this analysis was to first work with sea ice data and try to make a comparison of every ship through time and see how it interacted with the sea ice. If I take one day of sea ice, it may look like something like this. Now if I overlay all the ships for a certain year, that looks like the points you see in the background. And if I correlate just those ships that happen at the same time of that sea ice extent, I can then zoom in and then start plucking out those that are actually interacting with sea ice. We call these ship ice interactions. And through the entire 8-year time series, we've now mapped what ships have been doing with sea ice through time using this approach. Putting this in a kind of a perspective focused on Russia, you can see where most of the activity is. We have, over time, plotted who is doing this activity as well, and vastly it's the Russians. They're doing a lot of work on their northern coastline in the Arctic. They're building that infrastructure. In fact, if you sum up all the sea ice activity through the entire time series for all the countries, they don't equate what the Russians are doing right now. They have tools like this. If you know anything about the fleet of the US, we have one large-scale icebreaker, and it's 40 years old. And I've talked to the Coast Guard folks, and they said they've been asking for a new one for 40 years. I don't know if they're going to get that, but the Russians have about 40 of these things. This is the largest one in the world, nuclear-powered icebreaker. And this is what sea ice activity, ship ice activity looks like through time. You can see that, of course, as this ice gets thin and smaller extent in the summer, a lot of ships head to the Arctic and they start breaking ice, and then again they retreat in the winter. And in fact, if we start putting trend lines on this, we see that there's an increase of ships interacting with ice through the time series. So basically, the next steps for me is to start to validate some of this stuff, even more so than what we had. Again, my validation so far has just been with other satellite AIS data records. So I'd like to use some of the high-res optical imagery I've seen here. Every time there's a planet image of with ships and harbors and stuff, I get pretty excited. I wish I had access to some of that to start quantifying those ships and comparing it with what we can calculate. I'm interested in using some SAR data. And then I want to do some more data fusion other than just sea ice. There's other data layers like integrity of sea ice, thickness of sea ice, and so on. And then eventually we're going to start including this in a real-time data, so it'll be calculating all on the fly. And lastly, I hope to use this stuff to prioritize acquisition. So those highways that I was showing you in the Arctic, that could be prioritized areas for data acquisition in the long term. So that's it. Thanks.
All right, thank you. And if we could just get our last two presenters up into the hot seats again, and we can have one more round of Q&A. So if you have any questions, please step on up to the mic.
Both great presentations. My first question's for the Cropland Extent. Great that you're showing your users and producer accuracies and what they mean. It's possible I missed it, but as you're probably aware, those percentages can be particularly sensitive to the relative proportions on the landscape. So are you doing any effort in the training to ensure that your cropland and non-cropland proportions are appropriate to the landscape?
Absolutely, yeah. So in fact, there is various approaches to this accuracy assessment. First of all, just getting the random samples that we have collected from various sources, and second is scanning them for the type of things you said. What is the proportion if the cropland is 12% and other landscape is 88%. You can't have the same number of percentage of points for accuracy assessment. It's been well done in the sense taking all those into consideration. As I mentioned, this was done by Professor Russ Congleton, who is an authority in this, and you can read the detailed manuscript on this in LPDAC, how this was done. So, yeah.
Yeah, I'd like also to follow up on the Cropland Extent. I also had a look into the map and see extremely high accuracies, around 90%, for example, for Central Europe, and 90% is really, so I would say for land cover map is very accurate. However, I mean, usually when you see a new map, you go into your location or the locations you know, and then, for example, in Austria we have extremely high commission errors. Can you say something on the procedures or how it actually has been validated, and who did the regional validations, for example?
It's a very good question. When you do a global work and when you go to a local place and see, you should understand that it's a 1.873 billion hectares, and out of that, if you have 10%. That's not covered. It's still 183 million hectares. There's a lot of this one. But you have to understand one thing very important. That is, there is an overall accuracy. And in fact, I don't give much importance for overall accuracy at all, because as you said, it can be, actually the power can be pulled by the non-cropland, which is a high percentage of landscape. I give great importance for cropland, the cropland class accuracy, producers and users. So if you look at that, most of the places, you might have the commission error. When we have difficult areas, our idea was it's okay to have, like Australia I showed, 21% commission errors, but 99% omission, that means 1% omission error. That is because we trained our algorithm in such a way to capture all the croplands in Australia. So which implied that there is non-cropland getting into it. We are not too worried about that some non-cropland getting into it, for the simple reason in the higher level products you can get rid of that. So.
I was just talking about Europe, so Austria, not Australia.
Yeah.
So I was wondering for Central Europe. I mean, was there did you have people looking at regional accuracies? Because there, I mean, you're really in your validation. You can actually do interactually see these numbers. It seems that that also for this regional part you have quite high accuracies. Although
you have to really go into and see which exact part you are looking at. As I said, there are 72 error matrices, and Central Europe will have certain, I don't know how many numbers. You can take a look at that. But that team does not depend upon any one region. For example, when you are talking about sub-meter to 5-meter data, this is uniformly available for all over the world. It doesn't matter whether it is Europe or Africa or US. We have a set of interpreters, for example, who will interpret cropland, no cropland, and that is based on not one person interpreting it, but it's 3 people interpreting it, and only when everybody says yes, it gets into, as a data point for accuracy assessment. Otherwise, it gets dropped. So there is a lot of these kind of procedures that have gone into this, and so it's not done with any kind of, okay, now for this region, we want to have a low, it's good if some local people, and you are always welcome to provide feedback for us. If you see from some area, send me an email and say, okay, for this zone, or for this country, that's enough. So if you say this is my accuracy and this I don't, so, and just like the colleague here was just showing me that, there is a wetland that's mapped as cropland, that can happen, like, as I said, even out of this 1.83 billion hectares, if there is 180 million hectares that are really not being cropland, it's not worried. You can always have a second version where you can improve that, but probably you can't reach beyond a certain level in these kind of things. And that I'll be very happy if you can get anywhere between 90% ballpark, so.
Another question for cropland classification. Is that algorithm something that you can run repeatedly for subsequent years, or is it fine-tuned to the 2015 production?
Yeah, it's a very good question. We did a work on Australia, for example, using a 15-year run of the data set. And the most fascinating, and it's also published paper, and you can look at that for Australia from our website, that particular paper, wherein we generated for Australia using an automated algorithm. We actually developed it using a above normal year and a normal year and a below normal year. Developed that algorithm and then ran for 15 years what is cropland and no cropland. And it's an amazing thing that we found out that 2002 and 2008 were 2 of the worst 100-year drought years in Australia, and we did not pick looking at any data. We looked at it just by our coding, and then we looked at the climate data, and we were amazed. Why? For example, I don't remember whether it is 2002 and 2008. One of those years had 22%, 21 or 22% fallow, cropland fallow. Not only 22% cropland fallow, but also the existing cropland vigor had gone down by certain margin, if you look at an average. So that had a great impact on food security, and this was done automatically. Now, when it comes to cropland, no cropland, as long as you can set the same type of data sets, and if when you have, for example, if you change the number of bands, or if you change, for example, if you drop a particular index, and then your algorithm, you will have to account for that. Then, we share our code in most likely it will give you a first shot, and what you need to do is as long as you have if you run it on the same amount of data sets year after year, it will run. But if you change these parameters, it will have problem, and that is where you can say, okay, now then you have to write a code for that additional layer that you have.
Just a follow-up related question. You used several seasons to determine the cropland, no cropland. How did you separate those measurements into seasons? Because I guess that varies even within a single zone.
Exactly. Yeah. That's a very good question. For example, if you look at the phenology, for example, in US, in central, like let us say in Midwest, it is June to October, is the cropping season, or June to September. And if you go to Argentina, for example, it goes from December to March or something like that. So we looked at this phenology very carefully, and for every zone, we selected those months which fall into this phenological zone as one component. And of course, we had other months in the year as well, because they will have influence on how, for example, if you have in an area where you are growing 2 crops or 3 crops, you need to get that captured as well. So, but that means you might have a like monsoon season crop between June to October, and then Rabi season crop going from December to March or something like that. That also we capture. So, and also knowing whether it is irrigation or not. So all these factors, when we are coding for that particular region, this is where I mentioned that you need to have an intimate knowledge about croplands in particular zones. You can't just sit here in ivory tower and code it. So that's for sure. So the more knowledge you have about the field conditions, the better. Yeah. And we are lucky in that sense, just to add, that in our team, not only me, but lot of other people in working with us, like in consultative group for international agriculture centers, they are in the field. So we have them check and tell us what is happening.
Hi Prasad, I have a question about accuracy assessment again. One thing I've been wondering about with the current project is when you're going to select your points for accuracy assessment, especially the numbers of points, do you have a good statistical approach to figure out sort of the level of effort you need to put into coming up with a number of points so you have a high level of confidence in the accuracies that you're reporting, whether or not you're really truly just, reporting the true error of your map?
Yeah. There is this is a philosophy in itself. If you look at literature and if you talk to Russ, he'll say the thumb rule is that if you have a class, if you have a 50 points, it's good enough. But thing is, actually Russ and his PhD student did a lot of research initially when we started this project, wherein they came to a conclusion that for any zone, 250 points is for cropland versus no cropland is optimal, because beyond that you can add, it becomes, accuracy becomes asymptotic. You can throw in more points, it's not going to help. So 250 points, and in every zone we had far more than that. So
Area dependent, or if it's a larger area?
Exactly. So even with the larger area, that like even with the continental level area, they thought 200 beyond 250. Good 250 points, is what, like even in algorithms when you train, like for example, support vector machine and all, it's not, or even for random forest, it's not the number of points you have, it's the quality of the points you have. As long as you have good quality of points, when I talk about 250, it's the good quality of points that you have, that people are sure that this is cropland, no uncertainty, then you are firm even for a larger area. No, 250 for the zone. So cropland versus no cropland. But this is what the consistent results they got. Like 250 points. Beyond that, it didn't really help. Because the quality of the points itself were good. But if you have uncertainty in your data itself, then it causes a problem. Number of just the volume of data is not a consideration at all, in my opinion. That is why this mobile app, crowdsourced data set, I'm always skeptical, because especially to train your algorithm, because people don't know what they are sending, unless they are all kind of an expert like agriculture extension officers.
This question is for Greg. So at Planet, we've been kind of interested in maritime monitoring, I guess, for illegal fishing and other sort of national security purposes. I'm curious to what extent it's important in the Arctic being able to track ships that do not have AIS. So that's obviously where other imaging or other, information sources become invaluable.
So I think right now what we want to know is what percentage of ships don't have that. And if you remember from my chart showing the growth of number of ships through years, there was a big divergence between Class A and Class B. Class A are the big ships, and they have a steady but slow rise. It's the Class B ships that are growing fanatically, is the best way to put it. And most of those have not traditionally had AIS transponders, but because the technology has become cheaper and easier to access, more and more are. But it would be nice to use high-res imagery to start to validate this stuff and figure out what percentage of these ships currently have this and how that growth is actually happening.
Were those mostly like small fishing ships or personal
Class B,
craft?
small fishing ships and pleasure craft and so on. Yep.
For you, Greg, as well. So I'm interested in hearing your collaborations potentially with the Canadian Ice Service. What's interesting there is they have a huge and long archive of Arctic ice and all of the radar imagery for all of the Arctic.
Yep.
You'll see the ships, you'll see the ice, you'll see what's going on, you understand the classification of ice, you can actually start to predict where thin ice, new ice is, where ships are going to go and stuff like that. Are you thinking more forward in terms of, I'll call it predictive analytics or something else, something that we can say, how do we manage this going forward as opposed to what's happened in the past? I want to see, how do we manage the Arctic going forward? What's your thoughts on that?
Yeah, so right now the NSF has a call for future proposals, and it's called Navigating the New Arctic. And so we're in the process of writing a proposal for that call. And that will include some predictive analytics. And of course, we're trying to be as open as possible and work with any folks that have information. And included in this are the Coast Guard folks in Alaska who have a lot of ground-based AIS data, so they can mix it with our space-based. But we're really in the early stages of planning that proposal.
So Canadian Ice Service has been the main consumer of RADARSAT 1, 2. RCM is about to launch this year, so 3 more satellites.
Mm-hmm.
We will have a lot of data over the Arctic, and it will give us a very good mapping of where the ice is, what type of ice it is, as well as potential shipping routes. And as well, you'll get the observations of the ships. And by the way, RCM also has AIS on board as well, so you'll get
fantastic.
coincident imaging and AIS data as well. So
Yeah.
it'll be really good for validating, I think, the spoofing, the turning off the AIS, all the other things that people kind of worry about because AIS is
Right.
easily fooled.
Right. Yeah, I'd love to talk to you more about that.
Okay, great,
Yeah,
thanks.
yeah, thanks.
Any more questions for our panelists right now? No? Okay, well, once more, thank you for your participation.